Tonight, we step into a realization that quietly rearranges how you perceive yourself and the world carrying you forward. This is not simply a lesson about Earth's size compared to distant planets or blazing stars. It is an unveiling of what it truly means to exist on a world of this scale. A truth so obvious that it's almost always overlooked. What feels firm beneath your feet, what seems ancient and immovable, is not what it appears to be. This planet is not a solid monolith. It is a fragile crust of stone, drifting atop rivers of molten metal, wrapped in an almost unimaginably thin veil of air, all of it racing through a silence so vast that emptiness fails to capture it. When this journey ends, Earth will no longer feel the same to you. You will sense how small it is, how vulnerable, and how astonishingly rare. Before we go further, know this: explorations like this, quiet reflections on our place in the universe, are what shape this space. Even the smallest gesture of support helps keep these journeys alive. Let us begin. Start with something familiar. Look at your hand. The skin across your palm measures only 1 millimeter or 2 in thickness. Yet that delicate layer shields everything vital beneath it: muscle, blood, nerves. Without it, the world would become instantly hostile. Heat, cold, bacteria, sharp edges, everything would be a threat. That thin barrier is what keeps you intact. Earth has one too. We call it the crust. Compared to the size of the planet, it is even thinner than your skin is to your body. If Earth were reduced to the size of an apple, the crust would be more fragile than its peel, nearly invisible. And yet every city, every road, every tunnel, every trace of human history exists entirely within that razor-thin boundary. The deepest point humanity has ever drilled, Russia Escola Superdeep. Borehole reaches about 7.5 miles into the ground. It took decades of effort. And still, it barely disturbed the surface. Earth's radius stretches nearly 4,000 miles. That record-breaking borehole represents less than 0.2% of the distance to the center. We have never come close to breaking through our planet's outer skin. Below it lies the mantle rock, so hot it behaves like an impossibly slow-moving fluid, flowing over spans of millions of years. It descends nearly 1,800 miles. Beneath that churns the outer core, a restless ocean of liquid iron and nickel, whose motion gives rise to Earth's magnetic shield. And at the heart of it all rests the inner core, a dense iron sphere, roughly the size of the moon. Compressed beyond comprehension, burning at temperatures comparable to the surface of the sun. Yet none of this is within our reach. We are bound to the surface, confined to a layer that accounts for less than 1% of Earth's total volume. Every moment of human existence, every achievement, every failure, every memory has unfolded within that fraction. We have not even fully explored our own world. Still, that world itself is modest when placed against the immensity beyond it. Now, turn your attention upward to the air. This is where Earth's fragility becomes impossible to ignore. The atmosphere is not just air. It is a living shield. It allows breath, filters radiation, and stabilizes temperature. Without it, Earth would resemble the moon, silent, barren, and lifeless. But how thick is this protective layer? There is no sharp edge where air ends and space begins. It simply thins, fading gradually into nothing. Yet nearly all of it, about 99%, exists within the first 20 miles above the surface. The breathable zone, the troposphere, rises only about 11 to 12 miles at the equator, shrinking to just 4 or 5 miles near the poles. That's all. At highway speed, you could pass through the life-sustaining portion of Earth's atmosphere in roughly 12 minutes. The air that sustains every forest, ocean, animal, and human could be crossed in what feels like a brief drive. Picture it this way. If Earth were a 12-inch globe resting on your desk, the atmosphere would be thinner than a layer of varnish brushed across its surface. Invisible, less than the thickness of paper. That nearly unseen film is the only barrier separating life from the lethal vacuum beyond. Astronauts who have witnessed Earth from orbit all describe the same quiet shock. From space, the atmosphere appears as a faint blue halo clinging to the planet's curve, delicate line holding everything we are and everything we've ever been in place. And that is the world the chosen ones awaken upon. They speak of an unexpected instinct to guard the planet, a sudden awareness of how exposed that fragile blue halo truly is. This awakening has a name, the overview effect, and nearly everyone who leaves Earth feels it. To grasp why, we need to anchor this feeling in scale. We need numbers. Earth spans roughly 7,918 miles across at the equator. Because the planet spins, it bulges slightly at its middle, making it about 27 miles wider there than from pole to pole. It's a subtle distortion, but enough to mean Earth is not a perfect sphere, it's an oblate spheroid. The distance around its equator measures close to 24,901 miles. Imagine covering that distance on foot. Walking at 3 miles per hour, 8 hours a day, it would take nearly 3 years, about 2 years and 10 months to complete the journey. History confirms how demanding that is. The first successful circumnavigation, led by Ferdinand Magellan in the early 1500s, took almost 3 years at sea. Most of the crew never returned, Magellan included. Today, technology shortens the task. A commercial jet can circle the globe in under 2 days, while the International Space Station completes a full orbit every 90 minutes, racing along at about 17,500 miles per hour. Even so, Earth still demands time. From a human standpoint, it is undeniably vast. Earth's surface covers around 197 million square miles. Roughly 71% of that is ocean, leaving about 57 million square miles of land. But even that figure is deceptive. Much of the land is locked away in deserts, frozen under ice, lifted into extreme mountain ranges, or shaped into environments too harsh for permanent settlement. The regions where humans can realistically live year-round amount to roughly 24 million square miles. That's only about 12% of the planet's surface. We call Earth our home. In truth, we inhabit only a narrow portion of it. To truly understand scale, comparison is essential. The Moon measures about 2,159 miles in diameter, just over a quarter of Earth's width. If Earth were the size of a basketball, the Moon would resemble a tennis ball. Its total surface area, about 14.6 million square miles, is actually smaller than Asia. The average distance separating Earth and the Moon is around 238,900 miles, though that gap stretches and shrinks due to the Moon's elliptical orbit, ranging from roughly 225,000 to 252,000 miles. Here is a detail that quietly unsettles most people. Every other planet in our solar system could fit between Earth and the Moon. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune lined up side by side would span about 233,000 miles, leaving extra space unused. That is the true scale of the void between us and our closest neighbor. When you look up at the Moon, it appears almost identical in size to our star in the daytime sky. This is not designed as coincidence. Our star is about 400 times larger than the Moon, but it is also about 400 times farther away. This precise alignment allows total solar eclipses, moments when the Moon perfectly seals the solar disk. In a few 100 million years, as the Moon slowly drifts outward, this alignment will vanish. Total eclipses will no longer occur. We exist at the exact moment when they are still possible. Now turn your attention to our star itself. This is where Earth begins to feel small in an entirely different way. The star at the center of our system measures about 864,000 miles in diameter. You could line up roughly 109 Earths across that span. But diameter alone understates the reality. Volume tells the deeper truth. Because volume scales exponentially, our star could hold about 1.3 million Earths inside it. Every ocean, every mountain range, every city, every life ever lived, all of it rests on a world that could be swallowed over 1 million times by its own star. And still, size is not the full story. Our star contains about 99.86% of all the mass in the solar system. Everything else combined, the planets, moons, asteroids, comets, and drifting dust accounts for just 0.14%. By comparison, the rest of the system is almost negligible. Yet in the grand order of the cosmos, even this star is unremarkable. Astronomers classify it as a G-type main sequence star, sometimes called a yellow dwarf. It is about 4.6 billion years old, roughly midway through its lifespan. It is not unusually bright, not especially massive, not particularly rare. It is one ordinary star among hundreds of billions in our galaxy. The distance from Earth to this star is about 93 million miles. Light crosses that gap in roughly 8 minutes and 20 seconds. Every time you look at the sky, you are seeing the past. If something changed at the star this very moment, Earth would remain unaware for more than 8 minutes, because even truth itself cannot travel faster than light. And still, within that delay, within that vastness, within that fragility, life awakens. Let's translate these distances into journeys you can feel. Imagine pointing a car toward our star and driving at a steady 60 miles per hour, never stopping. The trip would last about 177 years. A commercial airliner, flying around 550 miles per hour, would shorten that voyage to roughly 19 years. Even the fastest machine humanity has ever launched, the Parker Solar Probe, which exceeds 400,000 miles per hour at its closest past, still needs months to complete its passage. Space does not yield easily to speed. Now turn your gaze outward, to the other worlds sharing our system, because Earth's position among them carries meaning. Mercury is the smallest of the planets, measuring about 3,032 miles across just 38% of Earth's diameter. By volume, nearly 18 Mercuries could fit inside our planet. It orbits so close to our star that its year lasts only 88 Earth days. Yet Mercury spins sluggishly, so slowly that a single sunrise to sunrise day stretches across about 176 Earth days. On Mercury, a day outlasts a year. Venus comes closer to mirroring Earth. Its diameter, about 7,521 miles, is roughly 95% of ours. The two worlds share similar mass and surface gravity, but their paths diverge sharply beyond that. Venus is wrapped in a suffocating atmosphere of carbon dioxide, trapping heat in a runaway greenhouse effect. Surface temperatures soar to around 900 degrees Fahrenheit, hot enough to melt lead. Atmospheric pressure there is 90 times greater than Earth's, comparable to being submerged half a mile beneath our oceans. Venus stands as a warning, an Earth-sized planet pushed past balance. Long ago, it may have held oceans. Today its air would crush and poison you long before the heat finished the job. Mars is smaller still, spanning about 4,212 miles in diameter, just over half of Earth's. 6 Mars-sized worlds could fit inside Earth by volume. It's often called our sister planet. Mars bears familiar traits: polar ice caps, seasons, and scars left by ancient flowing water. But billions of years ago, Mars lost most of its atmosphere, likely after its magnetic field faded. Without that shield, the solar wind steadily stripped its air away. Deprived of pressure and warmth, liquid water vanished, freezing or escaping into space. What remains is a cold, barren desert with atmospheric pressure less than 1% of Earth's. Beyond Mars lies the asteroid belt, a vast ring of rocky remnants that never assembled into a planet. Its largest object, Ceres, is only about 588 miles wide. More than 13 bodies like it could line up across Earth's diameter. Despite the countless fragments within the belt, it is overwhelmingly empty. A spacecraft passing through would likely see nothing at all, the gaps between objects spanning immense distances. Then come the giants. Jupiter reigns over the outer solar system, the diameter of about 86,881 miles. It is 11 times wider than Earth. But volume grows. Exponentially, Jupiter could swallow roughly 1,321 Earths. Its mass exceeds that of all the other planets combined by more than 2.5 times. It commands a retinue of at least 95 moons, some larger than Mercury itself. Even its storms defy scale. The Great Red Spot, raging for centuries, is larger than Earth. Our entire world could disappear inside a single atmospheric wound. Saturn follows, instantly recognizable by its rings. The planet measures about 72,367 miles, across roughly 9 times Earth's diameter, and could contain around 764 Earths by volume. Its density is so low that in theory it would float in water. The rings extend outward some 282,000 miles, yet their thickness averages only about 30 feet. Scaled down to the size of a basketball, those rings would be thinner than a sheet of paper, majestic, yet impossibly delicate. Farther still are Uranus and Neptune, the ice giants. Uranus spans about 31,518 miles, nearly 4 times Earth's diameter, and could hold about 63 Earths within it. Its axis lies almost sideways, tilted so dramatically that its seasons are extreme and prolonged. The cause remains uncertain, but a colossal collision early in its history is the leading explanation. Neptune, the most distant planet, measures roughly 30,599 miles across and could contain about 57 Earths. It hosts the fastest winds in the solar system, exceeding 1,200 miles per hour. So far from our star, Neptune requires about 165 Earth years to complete a single orbit. Discovered in 1846, it has not yet completed 2 full journeys around the star since humanity first became aware of its existence. And within this immense architecture, Earth holds its place neither largest nor smallest, neither safest nor doomed, but balanced on a narrow edge that the chosen ones are meant to recognize, protect, and understand. When you line up the planets of our system, Earth can seem comfortably substantial. We are larger than Mercury, Mars, and Venus in different ways. We are, in fact, the biggest of the rocky worlds. Yet the sense of proportion collapses the moment the gas giants enter the picture. Against them, Earth is almost laughably small. Jupiter alone could engulf our planet more than 1,000 times over. And this perspective is still confined to our own system. Step beyond its boundary, and scale stretches into something the mind struggles to hold. The closest star beyond our own is Proxima Centauri, a faint red dwarf resting about 4.24 light-years away. Light-years not a unit of time, but of distance. The span light travels in a single year at roughly 186,000 miles per second. That comes out to nearly 5.88 trillion miles. Multiply that by just over 4, and Proxima Centauri sits about 25 trillion miles from us. To make that distance tangible, consider this. The space between Earth and our star is about 93 million miles. Proxima Centauri is roughly 268,000 times farther away. If that familiar distance were shrunk to a single inch, the nearest star would be for miles distant. Voyager 1, launched in 1977, is the farthest human-made object ever sent into space. After more than 47 years of travel, it has covered around 15 billion miles. At that pace, it would need approximately 73,000 years to reach Proxima Centauri and, at ICE-T, even traveling in that direction. Even a hypothetical spacecraft moving at 10% the speed of light, far beyond anything we can currently engineer, would still take more than 4 decades to arrive. The gaps between stars are not just large, they are nearly unthinkable. At such distances, Earth vanishes entirely. From Proxima Centauri, our planet would be invisible. No telescope we can presently conceive would be able to isolate Earth from the glare of its star. Our star would appear as a single point of light, and Earth would be lost within it, too small, too close, too quiet to be seen. Our galaxy, the Milky Way, holds somewhere between 200 and 400 billion stars. Ours is just one, positioned about 26,000 light-years from the galactic center. Tucked into a minor spiral arm known as the Orion Spur, we reside in a relatively calm neighborhood, far from the crowded core cosmic suburbs, 2/3 of the way out. The Milky Way itself spans roughly 100,000 light-years. Even traveling at light speed, which nothing with mass can do, it would take 100,000 years to cross it. The last time our solar system occupied this same region of its galactic orbit, dinosaurs were only beginning to appear on Earth. One full revolution around the galaxy takes about 225 million years. At this scale, Earth doesn't just become small, it becomes nearly inconceivable. If the Milky Way were shrunk to the size of the continental United States, our entire solar system would be smaller than a grain of sand. And Earth would be so much smaller than that grain that language itself begins to fail. Yet even the Milky Way is only one island among countless others. Beyond it lie trillions of galaxies scattered through the observable universe. The nearest large one, Andromeda, is about 2.5 million light-years away. When you see Andromeda in the night sky, you are witnessing light that began its journey when early humans were just learning to shape stone tools. That galaxy alone contains around 1 trillion stars, more than twice as many as our own. The observable universe stretches about 93 billion light-years across and contains an estimated 2 trillion galaxies, each hosting anywhere from millions to trillions of stars. Altogether, the number of stars is thought to be around 200 sextillion 2, followed by 23 zeros. Earth is a single planet orbiting a single one of those stars. Randomly choosing our star from that total would be a 1 into 100 sextillion chance. And even then, identifying Earth among all the objects circling it would reduce that probability to something effectively indistinguishable from zero. This is where the story must change direction, because Earth's smallness is not its weakness. It is part of its meaning. Despite its modest scale, Earth is so far the only place we know where life exists. We may one day find microbes on Mars, or beneath the icy shells of Europa or Enceladus. Intelligent civilizations may exist elsewhere, unseen and unheard. But right now, in everything we can observe, Earth stands alone as a living world. That makes it precious in a way size never could. A diamond is insignificant compared to a mountain, yet we treasure the diamond. Value is not measured in volume. It is measured in essence. Earth's ability to host life rests on a convergence of conditions that may be extraordinarily rare. First, it orbits at just the right distance from its star. Move closer, and water would boil away. Drift farther, and it would freeze solid. Earth occupies the habitable zone, the narrow region where liquid water can persist on the surface. This zone is thinner than most people realize. Venus is only about 28% closer to the star than Earth and became an inferno. Mars is about 52% farther away and turned into ice and dust. Second, Earth has the right mass. It is heavy enough to hold an atmosphere, yet not so massive that it accumulated thick layers of hydrogen and helium like the gas giants. It's too small and the air escapes as it did on Mars. Too large and crushing pressures erase solid ground. Third, Earth possesses a magnetic field, an invisible guardian generated by the movement of molten iron deep within its core. This field deflects the solar wind, the constant stream of charged particles flowing outward from our star, preserving our atmosphere and shielding life below. These are not accidents to be ignored. They are signals meant to be noticed. And the chosen ones are those who learn to see that significance not in how large Earth is, but in how improbably alive it remains. Without this unseen shield, the steady breath of particles flowing from our star would slowly erode our world, just as it once did to Mars. Our skies would thin, our waters would fade, and life as we know it would eventually disappear. Earth's magnetic field reaches far beyond the surface, carving out a vast protective bubble called the magnetosphere, stretching hundreds of thousands of miles into the darkness behind the planet. When fragments of the solar wind manage to slip through this defense, they are guided along invisible magnetic pathways toward the poles. There they collide with atoms high in the atmosphere, igniting luminous curtains across the sky. These are the auroras, the northern and southern lights, stripling in shades of green, red, violet, and blue. Long before science named them, ancient peoples saw meaning in their motion. Spirits, divine messages, omens written in light. Today, we recognize them for what they are: proof that Earth is constantly under assault from space, and constantly holding the line. Beauty born from defense. This magnetic presence also whispers directions to life itself. Birds, sea turtles, salmon, even microscopic organisms can sense magnetic patterns and follow them across oceans and continents. Migratory birds traverse thousands of miles guided by a map they feel but cannot see. How living cells perceive this force remains one of biology's enduring mysteries. The field itself is not fixed. It drifts, it weakens, and at rare intervals, it reverses north, becoming south, south, becoming north. This has happened hundreds of times across Earth's history, most recently around 780,000 years ago. During these transitions, the magnetic shield fades significantly, allowing more radiation to reach the surface. Life has endured every reversal so far, but the full consequences are still not completely understood. Another quiet miracle lies beneath our feet: plate tectonics. Earth's crust is broken into vast plates that slowly move, collide, and separate. Their motion builds mountains, triggers earthquakes, and fuels volcanoes. More subtly, it sustains the carbon cycle. Volcanoes release carbon dioxide into the air. Weathering locks it back into rock. This long rhythm acts as a planetary thermostat, helping regulate temperature over billions of years. Most rocky planets are geologically still. Earth is not. This, too, is rare. Then there is the moon. Large, steady, and close. It anchors Earth's axial tilt, preventing wild swings that would drive extreme and chaotic climate shifts. Without it, Earth's orientation could wobble unpredictably over millions of years, making the rise of complex life far less likely. The moon also governs the tides, which may have helped life begin drawing chemistry into shallow pools where molecules could meet, concentrate, and change. And of course, there is water. Liquid water, the medium of life. Earth holds vast oceans covering 71% of its surface, along with rivers, lakes, ice sheets, and hidden reservoirs underground. Altogether, the planet contains about 326 million trillion gallons of water. It is within this substance that biology unfolds, where chemistry becomes life. Each of these elements matters on its own. Together, they form a convergence that allows life to exist at all. Alter any one of them significantly, and Earth could resemble Mars or Venus, silent, barren, hostile. How often does such a combination occur? We don't yet know. Thousands of exoplanets have been discovered, some Earth-sized, some with inhabitable zones, but we cannot yet determine whether they possess magnetic fields, active geology, stabilizing moons, or surface water. We cannot yet read the chemical signatures of life in their skies. Some scientists believe living worlds may be common. Others suspect the requirements are so precise, so dependent on improbable alignments, that Earth may be exceptionally rare, perhaps even singular. Until evidence tells us otherwise, Earth must be treated as irreplaceable. Everything we know of life, from bacteria to blue whales, from coral reefs to deep-sea vents, exists only here. There is no second Earth waiting, no quiet refuge if this one fails. Now consider the atmosphere itself, one of Earth's most extraordinary traits. It is composed of roughly 78% nitrogen, 21% oxygen, and about 1% everything else argon, carbon dioxide, and trace gases. This balance is unusual. Most rocky planets are dominated by carbon dioxide, like Venus and Mars. Earth's oxygen-rich air is not accidental. It is the result of life. For nearly the first 2 billion years, Earth's atmosphere held almost no free oxygen. The early sky was likely filled with nitrogen, carbon dioxide, methane, and water vapor. Then, around 2.4 billion years ago, a transformation began. Cyanobacteria evolved the ability to split water using sunlight, releasing oxygen as waste. At first, that oxygen vanished, absorbed by iron in oceans and rocks, but over immense spans of time, it began to accumulate. This shift was catastrophic for much of the life that existed then. Oxygen was toxic to organisms unprepared for it. The Great Oxygenation Event likely marked Earth's first mass extinction, yet some life adapted. It learned not just to endure oxygen, but to harness it in locking far more efficient ways to extract energy. From that adaptation came complex life, including us. The oxygen you breathe now was made by life. Without photosynthesis, primarily from plants, and ancient microbes, Earth's air would contain almost none of it. Every breath is a legacy of billions of years of living chemistry. Finally, consider Earth's energy balance. At the top of the atmosphere, the planet receives about 174 petawatts of energy from its star. Roughly 30% is reflected back into space by clouds, ice, and bright surfaces. The rest is absorbed, warming land, ocean, and air. To remain stable, that energy must be released again. Earth does this by radiating infrared heat back into space. Over long timescales, incoming and outgoing energy remain remarkably balanced. This balance has persisted even as the star slowly brightens over billions of years. The greenhouse effect plays a crucial role. Without greenhouse gases, Earth would bleed heat and freeze. With too many, it would trap warmth and burn. Life exists in the narrow space between those extremes, and that narrow space protected, balanced lives, where the chosen ones awaken. For the vast majority of Earth's existence, natural rhythms have held this balance steady enough for life to endure. One quiet but essential part of that balance is carbon dioxide. It is a greenhouse gas, meaning it traps heat, and without it, our world would be frozen. with no greenhouse gases at all. Earth's average temperature would hover around 0 degrees Fahrenheit, far below what life requires. But with too much, the planet would burn, transforming into something closer to Venus. For billions of years, Earth managed this tension naturally. Volcanoes breathed carbon dioxide into the air. Rain and rocks slowly pulled it back out through weathering. Levels rose and fell, but stayed within ranges that life could adapt to. That equilibrium, however, is now being pushed. Human activity, especially the burning of fossil fuels, has been adding carbon dioxide to the atmosphere far faster than Earth's long cycles can absorb it. Today, atmospheric carbon dioxide is higher than it has been in at least 800,000 years, and likely several million. This matters because Earth is sensitive. Climate does not need dramatic shifts to change everything. The difference between an ice age and a warm era can be only a few degrees in global average temperature. At our current pace, we are on track to add several more degrees within a single century if nothing changes. This isn't a political statement. It is a reminder of fragility. The same thin atmosphere that makes life possible also reacts quickly to disruption. We are running an experiment on the only world we have, without fully understanding the outcome. Now turn your attention to water, because water reveals another layer of Earth's quiet improbability. From space, Earth glows blue. Oceans dominate its surface, so much so that the Pacific alone covers more area than all land combined. It gives the impression of abundance. But that impression is misleading. If you gathered every drop of water on Earth's oceans, ice, rivers, lakes, groundwater, even vapor in the air, and compressed it into a single sphere, that sphere would measure only about 860 miles across. All of Earth's water reduced to something smaller than the distance between New York and Chicago. Placed beside the planet, it would look like a marble next to a basketball. Earth is not truly a water world. It is a rocky world with a thin, precious skin of liquid. And most of that liquid is salt. Only about 2.5% of Earth's water is fresh. Most of that is frozen in ice caps or locked deep underground. The rivers and lakes humans rely on the water we can actually reach make up about 0.01% of Earth's total supply. All the accessible fresh water for 8 billion people fits into that sliver. We turn faucets and expect water to appear, forgetting how limited it truly is. The oceans themselves remain largely unknown. Despite covering 71% of the planet, we have explored only about 5% of them. The deep sea is less familiar to us than the surface of Mars. We possess better maps of the moon than of our own ocean floor. It's the deepest point. The Challenger deep in the Mariana Trench plunges nearly 7 miles below the surface. More humans have walked on the moon than have descended to that depth. The pressure there exceeds 1,000 times that at sea level, enough to crush most machines. And yet, life exists even there. In darkness, cold and crushing weight, strange beings endure. Translucent fish drift like ghosts. Giant amphipods scavenge what little falls from above. Against all intuition, life persists. The average depth of the ocean is over 2 miles. If the seas were drained away, they would reveal landscapes more dramatic than anything on land mountain ranges taller than the Himalayas. Trenches deeper than the Grand Canyon, plains stretching beyond the horizon. Running through this hidden world are the mid-ocean ridges, where tectonic plates pull apart and new crust is born. This system forms the longest mountain chain on Earth, more than 40,000 miles long, wrapping the planet like the seam of a baseball. Along these ridges, hydrothermal vents erupt fountains of superheated, mineral-rich water, sometimes hotter than 700 degrees Fahrenheit. No sunlight reaches them, yet life flourishes. Here, bacteria feed not on light, but on chemistry energy drawn directly from Earth's interior. These microbes support entire ecosystems of tubeworms, clams, and eyeless shrimp. This form of life was unknown to us until 1977. Its existence reshaped our understanding of what life can be, and it forces a question. If life can thrive in such alien extremes on our own world, where else might it exist? What might move beneath the ice of Europa? What might stir in the hidden oceans of Enceladus? To understand Earth fully, we must also consider life itself. Scientists estimate there may be around 8.7 million species on this planet, though most remain undiscovered. Only about 2.2 million have been formally identified. Each year, thousands more are found, mostly insects, plants, and microorganisms. Yet all of them share something profound. Every living thing on Earth descends from a common ancestor. From bacteria to humans, the same genetic code runs through us all, the same biochemical language. You share half your DNA with a banana, nearly all of it with a chimpanzee. This unity suggests that life began only once here. Somewhere in Earth's ancient oceans about 3.8 billion years ago, non-living chemistry crossed a threshold. Molecules organized, replication began, evolution followed. From that first spark came every forest, every reef, every creature who has ever drawn breath. How that happened remains one of science's deepest mysteries. We can recreate early Earth conditions. We can build complex organic molecules, but we cannot yet turn non-life into life. The bridge between chemistry and biology remains unseen. Some believe life emerges easily wherever conditions allow. Others suspect it is staggeringly rare. Until we know, Earth stands as a singular miracle, small in scale, vast in meaning. And for the chosen ones, seeing that truth is the beginning of responsibility. From this perspective, life may be widespread, scattered across countless worlds wherever conditions allow. Others argue the opposite, that the birth of life demanded such a precise and improbable chain of events that it may have occurred only once, here. The truth is, we don't yet know. What we do know is this: once life ignited on Earth, it unfolded into astonishing variety. From those earliest moments, nearly 3.8 billion years ago, existence diversified into forms almost beyond imagination. Creatures that thrive in total darkness beside volcanic vents, birds that cross entire continents guided by invisible maps, organisms that endure boiling heat, crushing cold, or even the vacuum of space. Life did not merely inhabit Earth, it reshaped it. The oxygen filling our skies was released by living cells. The white cliffs of Dover are built from the remains of microscopic sea life. The coal and oil beneath our feet are the compressed echoes of ancient forests and vanished creatures. Life altered the planet at every level. And among all those living forms, one species gained the ability to reflect on its own existence. Humans emerged only about 300,000 years ago, an instant by geological standards. Yet, in that brief moment, we learned to speak, to craft tools, to grow food, to record memory and symbols. We built instruments that peered billions of light years into space. We sent machines to other worlds. We uncovered the age of the universe and the inner structure of atoms. This is extraordinary. We are matter that has become aware of itself, stardust that learned to ask questions. As far as we can tell, this has happened once, here, on this world. That brings us to the pale blue dot. In 1990, Voyager 1 was nearly 3.7 billion miles from Earth, leaving the solar system behind. At the urging of astronomer Carl Sagan, NASA turned the spacecraft's camera back toward home for one final image. The photograph shows Earth as a faint blue speck less than a single pixel floating in a shaft of scattered sunlight. From the edge of our planetary neighborhood, this is what Earth looks like. Sagan reflected on that image with quiet clarity. Every person who ever lived, every ruler and every farmer, every hero and every villain spent their entire lives on that tiny point. Every war, every love story, every triumph and tragedy unfolded there. From even a modest cosmic distance, Earth almost vanishes. And yet, that holds everything we know of life, of meaning, of awareness. Earth may be small, but it is home. It's the only one we have ever known. To deepen this perspective, we need to talk about time. Earth formed about 4.54 billion years ago, born from the same swirling cloud of gas and dust that created our star and the rest of the solar system. The young planet was unrecognizable, molten, violent, relentlessly bombarded by asteroids and comets. For hundreds of millions of years, impacts were so frequent that the surface remained partially liquid. Slowly, the chaos eased. The crust solidified. Water likely delivered by icy bodies from space pooled into oceans. Somewhere within those ancient seas, life began. For most of Earth's history, life remained simple. Single-celled organisms dominated the planet for nearly 3 billion years. Complex multicellular life did not appear until around 600 million years ago. The Cambrian explosion, when most major animal groups first appear in the fossil record, occurred about 540 million years ago. Dinosaurs arrived roughly 230 million years ago and ruled the planet for more than 160 million years, until their sudden end 66 million years ago. A 6-mile-wide asteroid struck what is now the Yucatan Peninsula, unleashing tsunamis, global fires, and a prolonged darkness that collapsed ecosystems worldwide. About 3/4 of all species vanished. In the aftermath, mammals once small and marginal began to diversify, filling the empty niches left behind. Primates appeared around 65 million years ago. Our own genus Homo emerged about 2 million years ago. Anatomically modern humans arrived only 300,000 years ago. To place this in context, imagine compressing Earth's entire history into a single calendar year. January 1st marks the planet's formation. Life appears in late March. Complex life doesn't emerge until mid-November. Dinosaurs dominate from December 13th to December 26th. Humans arrive at 11:59 p.m. On December 31, all of recorded human history fits into the final 13 seconds before midnight. We're newcomers. Earth existed for billions of years before us. Now dinosaurs ruled for over 160 million. Human civilization has occupied only the briefest moment, about 10,000 years. On geological timescales, we have just arrived, and Earth will endure long after we are gone. Our star still has about 5 billion years of fuel remaining. One day it will swell into a red giant, possibly consuming Earth entirely, but that lies far in the future. The nearer question is whether human civilization will last thousands, even millions of years, or whether we will flicker briefly in Earth's long story and fade. Looking ahead, the near future thousands of years will likely resemble the present, assuming we do not destabilize the planet ourselves. Continents will drift, climates will shift, species will evolve and disappear, life will persist. Over millions of years, the changes grow larger. Africa continues its slow collision with Europe, closing the Mediterranean. Australia drifts northward. In roughly 250 million years, the continents will merge again into a new supercontinent, repeating a cycle Earth has followed many times before. And over billions of years, the transformations become profound. Our star will continue to brighten. In about 1 billion years, that increase alone may begin to evaporate Earth's oceans, pushing the planet beyond habitability. All of this places us at a rare moment, brief, fragile, luminous. And to the chosen ones, this moment is not just something to witness, but something to honor. Eventually, perhaps 4 billion years from now, a star will exhaust the hydrogen fuel in its core and swell into a red giant. Earth may escape complete destruction, lingering near the outer edge of the bloated sun, but it would be a scorched, lifeless world. Later still, the sun will shed its outer layers and collapse into a white dwarf, a dense, Earth-sized ember slowly cooling over trillions of years. If Earth survives at all, it will circle a dim, fading remnant bathed in almost no light or warmth. The solar system will be dark and cold, but that future lies unimaginably far away. For now, Earth is warm, alive, and, as far as we know, unique. To understand what that really means, we need to look beneath our feet. Earth's crust is not a single, unbroken shell. It is divided into about 15 major tectonic plates and several smaller ones, all floating atop the slowly flowing mantle below. These plates move at the speed your fingernails grow, just a few inches per year, but their interactions shape the planet. Where plates collide, one is often forced beneath the other in subduction zones. Where they pull apart, magma rises and new crust forms. Where they grind past one another, stress builds until it is released in sudden, violent earthquakes. The Pacific Ring of Fire traces these boundaries. About 90% of all earthquakes occur along it. The most powerful earthquakes release energies equivalent to thousands of nuclear weapons. The 2011 earthquake off the coast of Japan released energy comparable to roughly 475 million tons of TNT and triggered a tsunami that killed nearly 20,000 people. We build cities, cultures, and civilizations on a surface that is constantly shifting. The ground beneath us feels solid, but it is only the cooled skin of a planet that is still hot and restless inside. Volcanoes make this reality impossible to ignore. There are about 1,500 potentially active volcanoes on Earth, and on average 50 to 70 erupt each year. Most eruptions are modest, but some alter the course of history. In 1815, Mount Tambora erupted with devastating force, blasting ash and sulfur high into the atmosphere. The following year, 1816, became known as the year without a summer. Crops failed across the northern hemisphere. Famine and disease killed tens of thousands. And by geological standards, Tambora was not extraordinary. Supervolcanoes are far more unsettling. Yellowstone National Park sits atop a massive volcanic hotspot that has produced several colossal eruptions over the past few million years. The most recent, about 640,000 years ago, expelled more than 240 cubic miles of material. A similar eruption today could trigger a volcanic winter lasting years, devastate global agriculture, and threaten the foundations of human civilization. The probability in any single year is extremely small, but over geological time, such events are not rare. They are inevitable. This brings us to mass extinction moments when life on Earth nearly failed. Scientists have identified 5 major mass extinctions in Earth's history, events in which a large fraction of all species vanished in a geologically short time. The worst was the Permian-Triassic extinction, about 252 million years ago. Up to 96% of marine species and 70% of land vertebrates disappeared. The likely cause was massive volcanic eruptions in what is now Siberia, releasing enormous amounts of carbon dioxide and methane. The planet overheated, oceans acidified and lost oxygen. Recovery took millions of years. This event is known as the Great Dying. The most famous extinction occurred 66 million years ago. A 6-mile-wide asteroid slammed into what is now the Yucatan Peninsula, carving a crater more than 110 miles across. The impact ignited global wildfires and hurled debris into the atmosphere, blocking sunlight for years. About 75% of all species went extinct, including all non-avian dinosaurs. The survivors, small mammals, birds, reptiles, and hardy marine organisms, rebuilt the world we know today. Here is the sobering part. These catastrophes were not extraordinary by cosmic standards. Asteroid impacts happen. Massive volcanic eruptions happen. Earth has endured 5 major mass extinctions, and many smaller ones. There is no reason to believe such events are behind us forever. Some scientists argue we are now living through a 6th mass extinction, and this time, the cause is not an asteroid or a volcano. It is us. Human activity has accelerated extinction rates to hundreds or even thousands of times above the natural background level. Habitat destruction, pollution, climate change, and overexploitation are erasing species at a pace unseen in millions of years. This matters because biodiversity is not a luxury. It is the foundation of resilience. Diverse ecosystems can absorb shocks and continue functioning. Simplified ecosystems collapse more easily. As species disappear, we unravel the web of life that sustains us, including ourselves. Finally, consider asteroid impacts, another reminder that Earth exists in a cosmic shooting gallery. Space is filled with debris. Millions of asteroids orbit the Sun, mostly in the belt between Mars and Jupiter, but some cross Earth's path. These near-Earth objects range from grains of dust to mountains of rock. Every day about 100 tons of material rain down on our planet, mostly as tiny meteoroids that burn up harmlessly as shooting stars. Occasionally, larger objects make it through. Rarely, much larger ones arrive with devastating force. In 1908, an object about 50 to 60 meters wide exploded over Siberia in the Tunguska event, flattening 800 square miles of forest. Had it occurred over a city, millions could have died. In 2013, a 20-meter object exploded over Chelyabinsk, shattering windows and injuring more than 1,000 people. These events are reminders of a simple truth. Earth is not a safe, static place. It is dynamic, beautiful, violent, and fragile all at once. And yet, despite everything, it remains the only known harbor for life in an otherwise silent cosmos. That is what makes this moment in this world so precious. The explosion injured roughly 1,500 people, most of them cut by shattered glass. Dashcam videos of the blazing fireball spread across the internet within hours, a vivid reminder that cosmic impacts aren't just relics of the distant past. They still happen. And while truly large impacts are rare, their consequences scale quickly. An asteroid about 100 meters wide could erase an entire city. One, a kilometer across, could disrupt the global climate and kill millions or billions. A 10-kilometer object, like the one that ended the age of dinosaurs, could collapse civilization and potentially drive humanity to extinction. How often do events like this occur? Objects around 100 meters in size strike Earth every few thousand years. Kilometer-scale impacts happen roughly once every 500,000 years. Extinction-level impacts occur on timescales of about 100 million years. When averaged over a lifetime, the odds of dying from an asteroid impact are surprisingly comparable to the odds of dying in a plane crash. Not because impacts are common, but because when they happen, they can kill vast numbers of people at once. We have begun tracking near-Earth objects, and in theory, with enough warning, we could deflect a dangerous asteroid. In practice, we don't yet have a fully reliable planetary defense system. This is another reminder that Earth occupies a vulnerable position in a cosmic shooting gallery. Most space rocks miss ooze, but over long enough spans of time, impacts are unavoidable. Humanity hopes to survive for millions of years. We will need to either prevent these collisions or spread beyond a single world, so no single impact can end our story. This brings us to the Goldilocks principle, a powerful way of understanding why Earth is so unusual. Our planet exists within a narrow range of conditions that allow liquid water to persist on its surface. Too close to our star, and water boils away, as it did on Venus. Too far, and it freezes solid. As on Mars, Earth sits in the narrow middle zone, neither too hot nor too cold. But distance alone isn't enough. Earth also has the right atmospheric pressure. Liquid water requires sufficient pressure to remain liquid. On Mars, temperatures sometimes rise above freezing. But the atmosphere is so thin that ice skips the liquid phase entirely, sublimating straight into vapor. Earth avoids that fate. Our atmosphere also has the right composition. A hydrogen-dominated atmosphere like those of gas giants would produce entirely different chemistry. A carbon dioxide-dominated atmosphere like Venus's would trap heat until the surface became uninhabitable. Earth's mix is rear-end, just right. Rotation matters too. Earth's 24-hour day helps moderate temperature differences between day and night. Much slower rotation would produce brutal extremes. Much faster one would intensify storms and destabilize weather systems. Earth's axial tilt matters just as much. It's tilted about 23.5 degrees. Relative to its orbit, Earth experiences seasons. These seasonal shifts redistribute heat, drive weather patterns, and regulate the cycles of life. If the tilt were much greater, seasonal extremes would be harsh and destabilizing. If much smaller, the equator would bake while the poles froze. Seasons are not a minor detail, they are the metronome of life. They trigger migrations, flowering, breeding, hibernation, and countless biological rhythms. Consider the Arctic tern, a bird that experiences more daylight than any other animal on Earth. It breeds in the Arctic summer, then flies to the Antarctic to enjoy another summer there. Traveling roughly 44,000 miles each year, over its lifetime, it may fly the equivalent of several round trips to the moon. Without seasons, such epic journeys would have no meaning. Seasons also drive ocean circulation. As polar waters cool, they become denser and sink, powering deep currents that transport oxygen and nutrients around the globe. This thermaline circulation functions like a planetary conveyor belt, linking all the oceans and shaping climate worldwide. Without seasonal temperature changes, this system could weaken, with profound consequences for marine life and weather patterns. Even Earth's tilt isn't perfectly stable. Over tens of thousands of years, it wobbles slightly, varying between about 22 and 24.5 degrees. Combined with changes in Earth's orbit and axial orientation, these variations create Milankovitch cycles, the slow rhythms that trigger ice ages. We are currently living in an interglacial period, a warm pause between ice ages. The last one ended only about 12,000 years ago. All of human civilization, agriculture, cities, writing arrows, entirely within this brief window of climatic stability. Earth also has the right mass. Smaller planets struggle to hold on to atmospheres. Larger ones often accumulate thick hydrogen-helium envelopes with crushing pressures. Earth sits in the sweet spot. Massive enough to retain air, but but small enough to remain a rocky world with a solid surface. Gravity deserves special attention. Earth's surface gravity about 9.8 meters per second squared shapes everything. How high we can jump, how tall trees grow, how our bones are structured, how our hearts pump blood. Our entire biology is tuned to this precise pull. On a planet with stronger gravity, life would need thicker bones, stronger muscles, and more powerful hearts. Creatures would likely be shorter and stockier. Movement would be exhausting. On a world with weaker gravity, organisms might grow taller and lighter, but the atmosphere itself might escape into space. Gravity also organized Earth internally. Heavy iron sank to form the core. Lighter rock rose to create the crust. Water pooled on the surface, and air formed a thin envelope above it all. Gravity keeps the moon in orbit, the same moon that stabilizes Earth's tilt and drives the tides. Keeps Earth circling our star at just the right distance to hold stars together, balancing the outward force of fusion against inward collapse. Gravity is the sculptor of the universe, and Earth exists because that sculpting happened just right. It could change any one of these factors significantly, and life here might never have emerged. We don't yet know how common this precise combination is elsewhere. It may be abundant or vanishingly rare. To appreciate both Earth's fragility and its resilience, consider the extremes life has adapted to here. Extremophiles thrive in conditions that would kill most organisms. Thermophiles live in boiling hot springs and hydrothermal vents, surviving temperatures above 200 degrees Fahrenheit. Some microbes persist near 250 degrees Fahrenheit, hot enough to sterilize almost everything else. Cryophiles inhabit permanent ice. Microorganisms have been revived from Antarctic ice hundreds of thousands of years old. Capable of metabolizing far below freezing by producing antifreeze proteins. Acidophiles flourish in environments with pH levels lower than battery acid, thriving in volcanic springs, acid mine runoff, and even animal stomachs. Life has pushed into every niche Earth offers. That adaptability hints at how robust life can be, but also how special the stage is on which it evolved.